Hello everyone, myself Dr. Ruchira Goel from Department of Applied Science and Humanities, Ajay Kumar Garg, Engineering College, Ghaziabad. Today I'll be taking partial differential equation, and the topic in the partial differential equation which I'll be taking is Lagrange's method. It is part of the syllabus of Maths 4. So moving ahead with the topic. The contents of the topic are solution of linear, quasi-linear partial differential equation of first order, that is Lagrange's equation. The working rule: a partial differential equation of the form capital P into this small p and plus capital Q into small q is equal to R. This capital P and capital Q and capital R, these are functions of x, y and z. For example, we have this equation yz multiplied by small p minus xz with q is equal to xy. So this is my capital P, this is my capital Q, this is my capital R. To solve this equation, we will apply the following procedure. We will form an auxiliary equation: dx upon P is equal to dy upon Q is equal to dz upon R. We will solve the auxiliary equation by method of grouping or by method of multipliers. So there are two methods, method of grouping or method of multipliers. Sometimes we will use both to get two independent solutions, u equal to a and v equal to b, where these a and b are arbitrary constants. So then the complete solution is given by some function of uv equal to 0 form, or in some cases it can be written as v equal to f function of u. So this is the general solution of this equation which we have taken, that is pp plus qq equal to r. Now to understand this concept better, what we will do, we will consider an example. So we will solve the following partial differential equation: yzp minus xzq equal to xy. So here, as I discussed earlier, this capital P, capital Q and capital R will be formed by comparison. So capital P turns out to be yz, Q turns out to be minus xz and R turns out to be xy. Now for writing the subsidiary or the auxiliary equations, we will consider dx upon P equal to dy upon Q equal to dz upon R, which implies dx upon yz is equal to dy upon minus xz is equal to dz upon xy. We have substituted the values of P, Q and R respectively in the auxiliary equation. Now from first and second fractions we get dx upon yz equal to dy upon minus xz. This z will cancel out on both sides, so we are left with dx upon y equal to dy upon minus x, which gives x dx plus y dy equal to 0. On integration, we get x square by 2 plus y square by 2 equal to c1 by 2. This c1 is a constant. This is a constant. So this 2 will merge with this, will cancel out on all the sides, and we are getting x square plus y square equal to c1 as one of the solutions. Now we require one more solution, as we have discussed in the working process. So we require one more solution. So let us consider the first and the third fractions. So when we consider the first and the third fractions, we have dx upon yz equal to dy upon xz. Now this y cancels on both sides. So this gives me dx upon z equal to dz upon x, which provides me with the equation x dx minus z dz equal to 0. If I integrate this equation, I get x square by 2 minus z square by 2 is equal to constant upon 2. Why we have written down this constant with 2? So that this 2 balances out on both sides. So hence we are having one more solution, that is x square minus z square equal to a constant. So the last solution, which was x square plus y square, and the second solution, which is x square minus z square, when written as a function equal to 0 form, which is the general solution, is achieved. So this is the solution of our given differential equation. Now, to understand the concept better, let us take one more example where we have y square z upon x into p plus y xz into q equal to y square. We rewrite this as y square z. We take this x here as well as here for multiplication, and we get y square z p plus x square z q equal to xy square. Now this will become my capital P, this will become my capital Q, and this will be my capital R. So for this equation, I get capital P as y square z, capital Q as x square z, and R as xy square. Therefore, the auxiliary equation becomes dx upon P is equal to dy upon Q equal to dz upon x upon R. So I substitute the value of P, Q and R to get these auxiliary equations. Now, logically, if I compare the first and the second equation, this and this equation, I am having x square dx equal to y square dy. Because what will happen when I consider these two equations, this z will cancel out on both sides and I am left with x square dx equal to y square dy. So on integration, I get x cube minus y cube is equal to some constant, because when I integrate x square dx is equal to y square dy, I'll get x cube upon 3 minus y cube upon 3 equal to constant upon 3, just as in the previous case, and obviously I'll get x cube minus y cube equal to a as the solution. This is my first solution. Now coming to the second solution. So I'll take the first and the third members of the equation. So from first and third members, let me recall what are the first and the third members. We have dy upon x square z equal to dz upon x, this is we have dx upon y square z equal to dz upon xy square. So this y square cancels out and we have x dx equal to z dz. So this is the same thing which we have written over here. We have x dx equal to z dz. So this x square minus z square equal to b is another solution on integration. Now this is my second solution. So from the first and the second solution, the general solution will be function of first solution comma second solution equal to 0 form. So this is my solution for the second example which I have considered. Now let us take one more example. So suppose I take pz minus qz equal to z square plus x plus y whole square. Now the question arises here, the given equation can be compared with pp plus qq equal to r. So as we can see, on comparison we get p as z, q as minus z, r as z square plus x plus y whole square. So the auxiliary equations are dx upon capital P, dy upon capital Q and dz upon capital R. We substitute the values of capital P, capital Q and capital R. Now, this is my first set of equations from which I'll take the first two members, that is dx upon z is equal to dy upon minus z I'll consider. So when I consider this, I'm left with dx equal to minus dy. So on integrating, I'll get x equal to minus y plus constant of integration. So I'm having x plus y equal to constant as my solution. So this is my first solution. This is equation number 2. Now again we will consider the first and the third fraction from these equations, which are auxiliary equations. So when I consider first and the third member, the first member is dx upon z and the third is dz upon z square plus x plus y whole square. So on comparing these, I get dx upon z equal to dz upon z square plus, since this x plus y whole square will interfere with our calculation, we will use equation number 2 to substitute this as c1 square. So now I have dx equal to z dz upon z square plus c square, which can be easily integrated. Multiplying 2 on both sides, I am having 2 dx equal to 2z dz upon z square plus c1 square, which on integration will give me log of z square plus c1 square. This is integration from this side, and this 2x I achieve from this 2 dx plus constant of integration. So I have log of z square plus c1 square minus 2x equal to c2 as one more solution. Obviously this c1 has to go away, so I'll substitute c1 as x plus y whole square. So the second solution turns out to be log x plus y plus z plus 2xy minus 2x equal to c2. This is my second solution. So I am having one solution as this, another as this one. So equation 2 and 3, they give the general solution as function of x plus y from the first solution, comma log x square plus y square plus z square minus 2x plus 2xy minus 2x equal to 0. Please remember, we do not consider these constants on both sides of the solutions in our general solution. We consider only the functional part. Now, let us discuss one more method, that is method of multipliers. As I have mentioned earlier, that this method of multipliers actually helps us to find out the solution to the Lagrange set of equations if in case the previous method of grouping fails. So this method says that we again have to find the auxiliary equation in the same manner as previous, that is dx upon p equal to dy upon q equal to dz upon capital R. Now in this L, M and N, these are multipliers which we will consider. They are our choice, and we have to decide what element has to be taken so that we can somehow make a pattern of this form. These equations or the ratios become equal to some L dx plus M dy plus N dz upon L into capital P plus M into capital Q plus N into capital R. This, while choosing this element, we have to remember that this entire value LP plus MQ plus NR must be taken equal to 0. So this L, M and N are chosen in a way that this entire expression is equal to 0. And thus L dx plus M dy plus N dz also turns out to be equal to 0. So to solve this equation, we will get the solution as u equal to some constant. When we solve this equation, we will get some solution equal to constant form. Similarly, another set of multipliers is chosen, and this new set of multipliers is mentioned to be L1, M1 and N1. And if the second solution turns out to be v equal to b, then we get the final solution of our set of equation, which was our problem statement, to be a function of u and v, that is solution which we achieved in the first case, and the second solution equal to 0. So, to understand this in a better manner, we consider an example or a question whereby we have x z square minus y square into del z by del x. This del z by del x is actually small p. Y into x square minus z square del z by del y. This is my small q. These are standard notations, small p and small q, for the derivatives of del z by del x. P is actually always del z by del x and q is always del z by del y. So, if instead of p and q we are having equation written in del z by del x and del z by del y, they serve the same purpose as small p and small q written over there. So, the right hand side is z into y square minus x square. Now, I can clearly see that this is my capital P, this is my capital Q, and this is my capital R. So, the auxiliary equations will be dx upon x z square minus y square, that is capital P, dy upon y into x square minus z square, that is capital Q, and dz upon z into y square minus x square, that is capital R. P, Q and R. We'll use multipliers x, y and z to get each fraction equal to x dx plus y dy plus z dz divided by x square into z square minus y square plus y square into x square minus z square plus z square into y square minus x square, which clearly takes this value of x dx plus y dy plus z dz as 0. Okay, so this x dx plus y dy plus z dz becomes equal to 0. So on integration, I get x square plus y square plus z square equal to constant. This is my first solution after taking x, y, z as multipliers. Now, what I'll do, I'll take one more set of multipliers to find the second solution. So to find the second solution, I'll have to choose 1 by x, 1 by y and 1 by z as the set of multipliers. So each fraction becomes equal to 1 by x dx plus 1 by y dy plus 1 by z dz upon the p value was x into z square minus y square, so that x cancels out. So that similarly plus x square minus z square plus y square minus x square we get. Let me write P, Q and R over here. My P was x z square minus y square plus x square minus z square. This was Q was y into x square minus z square and R is z into y square minus x square. So on multiply by 1 by x, 1 by y and 1 by z respectively, we get these three expressions. Their sum is turning out to be 0. Hence, the numerator must be equal to 0, which gives me on integration log x plus log y plus log z equal to log constant. Now, here I have considered this log so that this log on the left hand side goes away when I take anti-log on both sides. So, log of x, y, z equal to log C2 gives me the solution as x, y and z multiplied together equal to constant. This is my second solution. So, one solution I have got previously. Let me go to the previous page. This was my previous solution. This is first solution. And let me me go to the next page. This is my second solution. So I have written the general solution as xyz equal to function of x square plus y square plus z square as my answer. This is the entire solution. Now let us consider one more example. Let us have x into y minus z p plus y into z minus x q equal to z into x minus y as a numerical. So I'll write down capital P as x into y minus z, capital Q as y into z minus x, and capital R as z into x minus y. The auxiliary equations will be dx upon capital P, dy upon capital Q, dz upon capital R. So on substituting the values of these equations and choosing the multipliers as 1, 1, 1, I'll get this set of equations equal to dx plus dy plus dz divided by xy minus xz plus yz minus xy plus zx minus zy. Obviously, this is equal to 0. So, dx plus dy plus dz upon 0 is what I am achieving by considering the multipliers as 1, 1, 1. So, this is the set of multipliers which I have chosen this time. Now, dx plus dy plus dz will be considered equal to 0, as I have discussed earlier that the denominator, if it is 0, then numerator is considered equal to 0 to find the solution. So, I am on integration, I will get x plus y plus z equal to constant as my first solution. Now, again I will take multipliers as 1 by x, 1 by y and 1 by z. So, taking 1 by x, 1 by y and 1 by z as multipliers, I will get dx upon x into y minus z equal to dy upon y into z minus x equal to dz upon z into x minus y equal to dx upon x plus dy upon y plus dz upon z divided by y minus z plus z minus x plus x minus y, which turns out to be 0 again. This cancels out. And so I am left with 0 in the denominator. Now, again I'll consider the numerator equal to 0. So, integrating, we get log of x plus log of y plus log of z equal to log of constant, which gives me log of x, y, z is equal to log constant. The reason I have just told you to take log so that it removes when I consider antilog on both sides. This is my second solution. So, my general solution becomes function of x plus y plus z, comma, x, y, z equal to 0. The question may arise that in the previous question we have considered one of the solutions as function of another, and here I am writing function of two solutions equal to 0 form. It's your choice. If in this question also you may write x, y, z as function of x plus y plus z, but that form, function of one solution and second solution equal to 0, do exist. So, I am considering one more example to make my point. Find the general solution to the partial differential equation xp plus yq is equal to x minus y. This capital P is x over here, capital Q is y, and R is x minus y. So, the auxiliary equations become dx upon x equal to dy upon y equal to dz upon x minus y. This is my set of equations. I will consider the first two equations, dx upon x equal to dy upon y, which gives me on integration log x equal to log y. Obviously, I will take log constant as my constant of integration so that log goes away on both sides. So I am having log of x minus log of y equal to log of constant as my solution, which gives me log x upon y equal to log constant, and my general solution becomes xy equal to constant by taking antilog on both sides. Now, when I take antilog on both sides, I get the first solution. Again, to have the second solution, I'll use the multipliers 1, minus 1 and minus 1. When I take the multipliers 1, minus 1 and minus 1, I'll get dx upon x equal to dy upon y equal to dz upon x minus y equal to dx minus dy minus dz, because the numerators are each multiplied by 1, minus 1 and minus 1 respectively, and denominator turns out to be again equal to 0. And so this expression becomes equal to dx minus dy minus dz divided by 0. Now I'll consider this numerator equivalent to 0 as discussed earlier, and this on integrating I'll get the integration as x minus y minus z equal to constant. So this is my second solution. Now from equations 2 and 3, the general solution is function of first solution and second solution equal to 0. So this is a simpler task, and to let us complicate our p, q and r comparatively. So I have taken x minus y minus z square into p plus 2xy into q equal to 2xz as my question for the next case. So to write the auxiliary equations, I am having dx upon x square minus z square equal to dy upon 2xy is equal to dz upon 2xz. So here, if I consider the last two members, I'll get dy upon y equal to dz upon z. That means this equation and this equation will provide me with this set of equations whose solution is given by log y equal to log z plus log of constant. And so I get this as the solution, y by z equal to constant, as one of the solutions. Now we will use multipliers. So here we can see that, as I have mentioned earlier in the beginning itself, that both method of grouping and method of multipliers can be used sometimes. So here in this question we are using both. In the previous solution I have used method of grouping, and now I am using method of multipliers. So this dx upon x square minus z square, this set of auxiliary equations, I am taking x, y, z as multipliers. So I'll get x dx plus y dy plus z dz divided by x cube minus xy square minus xz square plus 2xy square plus 2xz square. Here we can see that this doesn't become 0 entirely, but this becomes equal to the denominator x into x square plus y square plus z square. Now what is the benefit behind taking this? Instead of 0, this is not becoming 0, but when I equate this equal to the third fraction dz upon 2xz, this x will go away. This entire expression will actually give me the numerator as a derivative if it is multiplied by 2. The numerator, if I multiply by 2, I'll get the derivative of the denominator in the numerator. So this denominator can then be integrated to give me log of x square plus y square plus z square, and obviously the left hand side equation dz upon z can be integrated to give log of z, and constant of integration is taken as log c2. So the solution I am getting here is x square plus y square plus z square divided by z, because this log comes on this side, and log of a minus log of b will be log of a upon b. So I'll get this second solution as x square plus y square plus z square. I'm using this result. and this log is taken anti-log, and this gives a by b. So this a by b form is over here. So I'm getting x square plus y square plus z square upon z equal to constant. Obviously, this is a solution. So from the second solution, which I have got on the previous page, x upon y by z equal to constant. This solution and the solution on the next page together give me the required general solution of the above equation. So this question is particularly important because here I've used both the methods, method of multiplier as well as that of grouping, and I'm not making the denominator as 0. So thank you very much for being with me.